Thank you so much. Okay, I would like to thank the organizers for giving me the opportunity to speak at this conference in this beautiful city with such an important mathematical history. I will speak about my young work with Fernando, with Albiac, about uniqueness of unconditional basis. Okay. First, we have to make clear the meaning of uniqueness. Well, if we have an unconditional basis and we rescale it, we get a new unconditional basis. So in order to get a uniqueness result, we have to restrict ourselves to normalized basis. Also, of course, we have to consider uniqueness up to equivalence, and unless the space has a asymmetric basis, we have to consider uniqueness up to a permutation of the basis. We point out that unconditional basis and atomic lattices, lattices over a discrete set, are the same thing. Are different ways to looking at the same mathematical object. In fact, if we have an atomic lattice and we consider its unit vector system, this system is an unconditional basis of the space, and the other way around. If we have an unconditional basis, this basis induces a lattice structure on the space. So in this talk, we will speak about atomic lattices over a discrete set. Okay. Most Banach spaces fail to have a unique unconditional basis. We have to take this into account. For instance, this isomorphism between LP and the direct sum in the sense of LP of n-dimensional Hilbert spaces, this isomorphism prevent LP from having a unique unconditional basis unless P is 1, P is 2, or P is infinity. In fact, Hilbert spaces, L2 has a unique unconditional basis. This is a classical result by Ketty and Teplitz. Also, L1 and C0 have a unique unconditional basis. Lindeström and Pełczycki obtained this result as a consequence of their study of Skripal-1 spaces. Okay, if we wonder for more Banach spaces with a unique unconditional basis, it is natural to look at direct sums of spaces with a unique unconditional basis. So these questions naturally arises. We have a Banach space X, another Banach space Y, both with a unique unconditional basis. If we wonder whether this direct sum has a unique unconditional basis. Also, we could look at infinite direct sum. We have a Banach space X with a unique unconditional basis, a lattice L with a unique unconditional basis, and we wonder whether the vector value of the space L of X has a unique unconditional basis. And finally, we also look to complementary subspaces. We have a Banach space with a unique unconditional basis, again, a complementary subspace of X, we call Y, this complementary subspace, and we assume that Y has a unique unconditional basis, has an unconditional basis, and we wonder whether this unconditional basis is unique. The first results in this direction appear in a paper by Edelstein and Wojtaszek. They prove that any finite direct sum constructed from L1, L2, and C0 has a unique unconditional basis. Later on, Burgen, Casaccia, Lindeström, and Zafriri, in their classical memoir, studied metric spaces constructed from C0, L1, and L2. And they proved that these spaces L1, L2, C0, L2, C0, L1, L1, C0 have a unique conditional basis, and also that its complementary subspace inherit the property. In the memoir, appeared some unexpected results. For instance, they proved that L2 of L1 and L2 of C0, the product, fail to have a unique and conditional basis. No? And also they found a space that is not constructed from C0, L1, and L2 that has a unique and conditional basis. This space is the two convexified Silerson space. So in light of the result by Bourgain et al., we claim that it is hopeless to try to classify Banach spaces with a unique and conditional basis. Total classification seems to be impossible. Okay, further advances appear in several papers by Casaccia and Carlton. They prove that the Silerson space and the original Silerson T and the original Silerson space T star, the dual, has a unique and conditional basis. They also prove that Nakano spaces, also known as variable exponent Lebesgue spaces, associated with a sequence converging to one, have a unique and conditional basis as long as they are lattice isomorphic to S square. This property, being lattice isomorphic to S square, is a technical condition, but is also important in all proofs that a given space has a unique and conditional basis. Of course, this sorry, well, no matter. I will continue. They solve in the negative one of the three general questions I posed in the previous slide. They found a space X with a unique and conditional basis, and uncomplemented subspace Y with an unconditional basis that fails to be unique. In fact, the space X is not an ordered space, but it's a complementary subspace of an ordered sequence space. And they also solved a question posed in the memoir. They proved that C0 sum don't preserve uniqueness. Bourgain et al. Proved previously that L2 sum don't preserve uniqueness, but they found this spaces C0 of T and C0 of T of T2, the two complexified Silerson space that fail to have a unique and conditional basis. To be honest, not much more is not about Banach spaces with a unique and conditional basis. Well, this is a recent advance. We proved that L1 C0, T star, L2, and T2, and spaces constructed as finite direct sum from these spaces have a unique and unconditional basis. Probably the most significant space in this list is L2 plus T2, because the previously achieved technique, the previous of the classic, don't work for this space. The general question about finite direct sums is open as far as we know. More question in this area. Well, a lot of questions are open, are still open. I highlight some of them. We don't know whether L2 sum and L1 sum of these Silerson spaces have a unique conditional basis. The behavior of infinite sum with three levels is unclear. For instance, we don't know whether C0 of L1 or L2 has a unique and conditional basis. And the behavior of Nakano spaces associated with a sequence converging to 2 is also unknown. Okay. But if we also consider quasi-Banach spaces, a lot of spaces with a unique and conditional basis arises. Probably the third result is the result by Carlton. Carlton proved that any sequence early sequence space associated with certain early functions have a unique conditional basis. In particular, this work for LP, for p less than 1. Carlton hypothesis proved that metric spaces LP of LQ with P and Q both less than 1 have a unique conditional basis. And hypothesis proved two things. Proved that this Hardy space has an unconditional basis, and later on, hypothesis proved that this basis is unique. It's the unique conditional basis of the space. The spaces in this slide are some common properties. All spaces are L-convex. Being L-convex means that either lattice Q-convex for some Q. This is a very natural condition. In a sense, we have to consider pathological quasi-Banach lattices that are not L-convex. And a property that defines them better is being strongly absolute. The definition of strongly absolute lattices is this inequality. This inequality, roughly speaking, means that the north of the lattice dominates the L1 north, and the north of the lattice is far from the L1 north, in the sense that if the L1 north and the north of the lattice are comparable, then the L1 north and the L infinity north are also comparable. This is, in a sense, these lattices are far from L1 and for a Banach space. So the specialist try to understand the behavior of quasi-Banach space that are not so far from a Banach space. That the behavior of spaces that have a Banach component. And several authors, through several papers, prove that these metric spaces have a unique and conditional basis. L2, C0T, LP0, L1 of LP. And there is a missing space in this list. It is unknown whether L2 of LP, or P less than 1, has a unique and conditional basis. When dealing with uniqueness problem, we have to manage subbases of the canonical basis of the space. So the lack of understanding of the subbasis structure of the space is a drawback to getting unique results. For instance, the subbasis structure of all spaces in the previous slides have a quite easy subbasis structure. No? This result, in a sense, allows us to manage spaces with a tricky subbasis structure and obtain new uniqueness results. This result says that if a basis XX, we have two bases, X and Y. If XM is a subbasis of YM, then we can cancel the powers and obtaining that X is a subbasis of Y. In a sense, it's a power cancelling principle. Okay. Some result that we can obtain using, in particular, this principle. Well, for instance, this one. This one says that certain infinite sums in the sense of an strongly absolute lattice have a unique unconditional basis, and this theory in particular solves a question about Banach envelopes. The Banach envelopes of a quasi-Banach space is the Banach space that is closest to the quasi-Banach space. For instance, the Banach envelope of LP for phi less than 1 is L1. And in all the above spaces, quasi-Banach spaces with unique and unconditional basis, satisfy that also the Banach envelope has a unique unconditional basis. Okay, but in this list, there is a space, LP of T star, with a unique unconditional basis, whose Banach envelope L1 of T stars fail to have a unique unconditional basis. Another theorem that, in particular, among other techniques, use the power cancelling principle is this one. This theorem is similar to the previous one. They also say that certain sums in the sense of an strongly absolute lattice have a unique unconditional basis, but these spaces are quite different from the spaces in the previous slide. These spaces are sufficiently Euclidean. This means that the space contain uniformly complemented copies of final dimensional Hilbert spaces, and the spaces in the previous slide don't have this property. They are anti-Euclidean. The point is that most Banach and quasi-Banach spaces with a unique unconditional basis are anti-Euclidean, and this theorem gives new sufficiently Euclidean spaces with a unique unconditional basis, in particular some classical spaces such as Hardy spaces with values in a Hilbert space. Okay, finally, I will talk about the squares of bases. All the spaces I consider have the property that are isomorphic to its square, and this property is important in the proof that this space have a unique unconditional basis. Okay, we have found a Banach space that is not isomorphic to its square and still has a unique unconditional basis. This space is the space that Gower used to solve the hyperplane, Banach hyperplane problem. Gower's space is not isomorphic to its square. Gower and Morey proved that in I don't remember the year, after Gower paper, and we have proved that it has a unique unconditional basis. And finally, there is another question related to the lattice convexity of the spaces. Given a Banach lattice or an convex quasi-Banach lattice, we can consider the indices P so that the lattice is P convex. And then in all the about cases, in all the about spaces, the supremum of this indices P is or less than 1, or 1, or 2, or infinity. Okay, we have proved that this optimal index sigma can be any P. In fact, not only Gower's space, but also P convexified Gower's space for P greater than 1 have a unique unconditional basis, and the optimal convexity of these spaces is P. I think that's all. This is my founder. Thank you very much.